right, so our guest speaker of the day this month is Professor Justin McCaulin. Justin is a multidisciplinary physicist currently serving as the orbital mechanics data specialist and researcher for the American Data Science, with over 2 decades and experience in the field. He also holds current roles as adjunct instructor in physics and astronomy at both University of Houston Clear Lake and the Houston Community College. Justin earned his master in physics from the Portland State University in 2005 and recently graduated with a postgraduate certification on AI and machine learning from the University of Texas in Austin. So his research integrates high-energy astrophysics with modern data science. So focusing on complex environments like the Orion Nebula, a dedicated science communicator. Justin is a long-standing member, and so he just told me more than 20 years already with our club, and frequent presenter at Fort Bend and the Houston Astronomical Society. So Justin, would you like to tell us everything about the jumbos and Orion?
The Orion Nebula, we all look at the Orion Nebula and we just think about, we have all the gas, and we think of the trapezium, and we get images like these, and they tend to be very cool images. But the thing about the Orion Nebula is that there's, particularly in the last 10 and 20 years, particularly with the James Webb Space Telescope, we are getting more information about the Orion Nebula, especially in the last 10 years than we've had in the previous 50 years of telescopic astronomy. Some basic facts: it's located in the constellation of Orion. There's always been an issue about its distance because the difficulties of trying to measure nebulous gases over vast distances. Usually what you do is you deal with the stars, particularly in the trapezium. You measure their distances from Earth, usually using a variety of different methods, and then you get some sort of like a value, and this is roughly within about an uncertainty of about 150 light years, so about 1,344 light years. What makes it stick out is that it's one of the most prominent stellar nurseries in the Milky Way galaxy, excluding the zone of avoidance, which is on the other side of the Milky Way around Sagittarius that we cannot see. It is rivaled by a few other nebulous groups, but the Orion Nebula really stands out in terms of lots of star formation and every indications of tremendous formation of planetary systems. Now, the visible part that we see is M42 and M43. We also have all this dusty material. It's mostly of hydrogen gas. There was an astronomer, Nicolas Claude de Peyragues, who actually observed this in 1610, noticed it as a nebulous object in a telescope. Of course, it wasn't the term nebula. He described it sort of like a mystery cloud of stars, like a hazy, fuzzy, gigantic fuzzball of a star. But really the term of nebulae would not be applied to these objects until around the 18th century. There's just enough material in this nebula to last for a few million years in the rate of star formation. But it's not like all this gas and dust is going to turn to 100% stars. Because once you reach a certain number of stars forming in a nebula, the radiation pressure is going to push all this dust and gas and dissipates out into space. Now, one thing is that it's about 2,000 times the mass of the Sun when we're dealing with this part of the Orion Nebula. So we have lots of material in here. It's spread out over many, many hundreds of cubic light years of space. In fact, if you look at the volume, it's about 10,000 light years, I should say about 10,500 cubic light years based on a diameter of 24 light years from the center. What do we mean by the center? Using the Trapezium star group as an example. The density is pretty low, though. You have to remember that in the Earth's atmosphere, we have billions and trillions of atoms and molecules per cubic centimeter of atmosphere, but it's 600 atoms. That doesn't look like it would have 600 atoms per cubic centimeter, but remember, we are staring at this nebula from over 1,000 light years, and if you were to venture through it, it would look pretty dark, because this is just the accumulation of looking at all that light, looking at an object that's very far away, that's dozens of light years across, and if you were to actually fly through the nebula, it would actually appear very dark and dim. Now, the trapezium, I'm sure we're all familiar with that. One thing is that there's actually there's A, B, C, D, E, and F, and then there's G and two H's, H1 and H2, and an I star. So there's just under 10 major stars that make up the trapezium, but really the four monstrous stars are A, B, C, and D. And around here, you're getting about 6,000 members that are now gravitationally bound to these four central stars. There's the E and F star. And so it's a very densely packed open star cluster. Part of it is actually covered up by the nebulous material. So you have to observe it in infrared to pierce this dust to see the rest of the members. Now, this is the entire, what we call the Eridanus Orion Nebula complex, because here's the Eridanus loop. This is, of course, is the river of ancient Mesopotamia. Here's the Orion constellation. The only thing that's not part of this great Orion-Eridanus super bubble is the Lambda Orionis ring, right here at the head of Orion. So right here we actually have the Orion Nebula, and right up here would be what we call one of the Barnard objects around the three stars that represent the head of Orion. This is actually not part of the super bubble. Its distance, the velocity of the gases, and the slight amount of hydrogen to other metals differs from the rest of the bubble itself. So this is looking from Orion from a greater perspective. So the overall shell of gas is about 1,000,000 Kelvin. Now, how do you measure the temperature of the gas? We have to measure the energy of the gas particles. So the more energy the gas particles have, the higher the temperature. And it's on a scale of hundreds of light years. Most of this is being lit up by the O and B stars. Those are the very massive, hot blue giant stars at the very large end or the heavy end of what we call the Hertzsprung-Russell diagram for main sequence stars. And they're on a scale of 80 to 100 suns. So we're dealing with some of the most massive stars that we can find in the Milky Way galaxy. The energy output from the stellar winds are on the scale of about 10 to the 44th joules. So imagine taking the entire energy produced by a 10 billion year lifespan of the sun and radiating that every second. So it's a very intense environment. And all this is released from these primarily from the supermassive O star, that would be Trapezium A, every few seconds. So it's just an intense amount of solar radiation. And the energy itself is pushing this gas at such a high speed. You all know about escape velocity. When you have escape velocity, a vehicle, if it's traveling fast enough, can escape out from the surface of the Earth out into space. Well, there's actually an escape velocity for the Milky Way galaxy. So this material is escaping out at hundreds of thousands to about a few million miles an hour. And that's enough for this material to actually escape the gravity well of the Milky Way galaxy and escape out into intergalactic space. So this material is moving so fast, it's overcoming the escape velocity of even for the Milky Way galaxy. Now, what are facts about the bubble itself? Well, the bubble is actually further away. The bubble itself does not reach all the way towards Earth. There's still about a distance of about 500 light years between our local bubble. We're actually in a local bubble of dust and gas that is higher in density compared to all the vacuum of space, the more emptier regions of the interstellar winds in the Milky Way galaxy. And then you go another 500 light years, and then you get into the bubble itself, and it's 1,200 light years across. In here, there's a lot of dark nebulas. There's multiple stellar nurseries. I mean, what do we have here? Well, we got Barnard's Loop. And then, of course, you've got right around here, you have the Horsehead Nebula, the Flame Nebula, and then there is a planetary nebula right here. And then there's the Reflection Nebula, and there's the Running Man Nebula down here. So there's a lot of nebulous regions. Part of the Witch Heads Nebula, is everybody familiar with the Witch Heads Nebula? That's actually being lit up as a reflective nebula from the light of Orion, from the light of Rigel. That's over here. And lots of open star clusters that have literally been shot out by the tremendous energy from the radiation that in some cases overcomes the gravity pull of these stars and are actually pushing these globular clusters, these open star clusters away from the formation region right here. So we can actually look at this. This is actually the Witch Head Nebula right here. So this is something with long exposure photography. You can actually get this in skies where you can actually have pretty clear views. You get very low bortle skies, Bortle 1, Bortle 2 skies just after sunset, and you get a view of it right here. And there's the Witch Heads Nebula, which is actually located right here. It looks a bit different because we're seeing this in a different wavelength of radiation, whether it's radio or infrared. Sometimes the nebulas that we see in visible light don't quite match what they see in infrared and in radio because of different structures that stick out. Here's some of the data that we're actually getting, particularly when we're looking at the complexity of the chemistry of the Orion Nebula itself. So we got a lot of water-based and organic compounds, a lot of precursors to life. There's mostly hydrogen and helium, but we get a lot of carbon, nitrogen, as we would expect to form in stars. All the oxygen, there's no free oxygen here. Well, there's a little bit of molecular oxygen, but the rest of it tends to bound with carbon monoxide, water, and we got methyl, we got methyl ketones, and formaldehyde, some of the precursors for forming RNA molecules, lots of exotic compounds, lots of neon. So we have a survey of the starbursts coming from the Hubble Space Telescope back from the 1990s. This region right here, this is what we call the Orion bar. I don't know if anybody's ever seen that in a telescope. Well, if you ever look at the central area where you have the trapezium, you get the central light patch within the inner part of the Orion Nebula, and you come across this bar right here, this sort of difference between the light and the dark regions. That's going to be the Orion bar. And right here, this has been an intensive study, particularly looking at the high concentration of protoplanetary disks being formed, a high concentration of what we call these methyl ketones, which basically you get the radiation striking the gas, it's breaking up the molecules, they're sort of recombining themselves, and that's the precursor for forming very complex organic molecules. And here we got a tremendous amount of ultraviolet radiation. It's what we call here called photorecombination. So basically, you get an atom that has a lot of electrons. You get a molecule where you have lots of atoms with lots of electrons. And they get a lot of high energy photons coming from the stars in the trapezium right here, a lot of ultraviolet photons. So they break up the atoms and they reconfigure the atoms, and you end up having something like carbon dioxide and methane and turning it into a lot of complex organic molecules, all forming in different layers as the radiation sort of breaks up the dust and creates these different barriers for which you can penetrate at different frequencies of infrared radiation when exploring the Orion bar. So there's the Orion bar itself. Now inside the Orion bar, we actually are photographing red dwarf stars forming. So we get a lot of material here. We have the thing about it is that the material swirls around the red dwarf stars, and it's sort of like the red dwarf stars are like a little gravitational drain. They immediately take the immediate dust and gas around them. They fall into the gravity well of the red dwarf stars, and they pop up pretty quickly. The one thing about the radiation from this nebula is that it breaks up the dust into little nodules, and it creates a much greater frequency of red dwarf stars being formed over all other types of stars. In fact, about nearly 76% of all the stars in the Milky Way galaxy, based on looking at the stellar neighborhood and now evaluating nebulas that are over 1,000 light years away, tend to be red dwarf stars. And one thing about the O and B class stars is that they're very rare. I mean, you get like maybe one for every several billion red dwarf stars. In those O and B class stars, there's an intense amount of ultraviolet radiation from the trapezium. And that radiation is going to dissipate all this material within just maybe around 3 to 5 million years. And that gas itself, the dust turns into gas. You've got basically photofluorescence, where basically the ultraviolet radiation stimulates the electrons and atoms, and what it does is it breaks up dust molecules and turns them into individual molecules and atoms, and you're basically undergoing sublimation of a dust to a gas. There's much that's unknown about how these methyl ketones are forming, but basically you have something like a molecule of methane, you take away one hydrogen atom, it's charged up, and that becomes the building block for creating your complex molecules, basically the basis for life. So right here, the primary driver is photochemistry, just lots of photons recombining hydrogen and carbon, combining it with oxygen. You get what we call a lot of endogenic reactions. Basically, they're absorbing the stellar energy. They're absorbing basically the starlight, the photons from these stars. The energy builds up, it messes around with the electrons, and it just recombines the carbon and hydrogen as the precursor for forming these molecules. It's the far ultraviolet radiation. It has to be very high ultraviolet radiation to have this effect. It's not like you can use low energy ultraviolet light that may shoot out 1 or 2 electrons, but actually stimulate them between the different layers within a cloud of electrons. But if you want to really break the bonds between atoms and really break up the electron clouds between atoms, you got to use the far ultraviolet radiation. And this is probably due to a lot of methane and hydrogen ions. So basically what you do is a hydrogen atom is stripped of electrons. It only has 1 electron orbiting around a proton. So every proton roaming around the universe is a hydrogen ion. And they interact with methane, and that's where you get these catons, these sort of positive charged, basically what they call polyatomic ions. So you got multiple atoms that have a net charge, and that just creates these complex organics. All right, so let's look at recent supernova and giant cavities. So there has been a 3D reevaluation of Barnard's loop. So right here, this is data from the GAIA spacecraft. So these are the huge voids of dust and gas. These are the huge cavities right here forming in the Orion region. The blue is the hot gas. The dust itself, evaluated in 2 dimensions, is the yellow areas. This is the tracer from the high energies from what was once a supernova explosion that occurred in the Orion Nebula. And what we find is that we can match the motion of star clusters from the original bursts. So you get earlier generations of stars forming star clusters. You get a huge burst of one of the big giant stars becoming a supernova blast. And that leaves literally a trail of open star clusters literally falling behind the Orion Nebula in their orbit around the Milky Way galaxy. Now, looking at the pathway of the radiation, looking at the concentration of the dust, and knowing a bit about studying nebulas by astronomers for decades, they find that many of these supernova events have occurred in the last 3 million years. So it's added a bit of dynamics to the nature of the Orion Nebula region. Right here is Barnard's Loop, Orion B, Orion A. These are just simply groups of nebulous material around the shock wave of all this dust around that original supernova blast. Okay, so now we can look at this in different frequencies of radiation. So we get the high energy right here. Here we get the hydrogen alpha right here in the blue. The purple is aluminum-26. So usually when you have an aluminum, a type of aluminum, it's highly energetic. It emits a lot of high radiation, particularly a lot of X-rays. And that tends to be the tracer from enormous stars that produce a lot of aluminum-26. And that high energy emits a lot of radiation pressure that will move out the material, particularly the dust around here. And then we see the hydrogen alpha gas, and you see this gap right here. That's all that aluminum-26 with its radiation literally pushing out the gas and pushing out the dust because it gives it enough energy to where it overcomes gravity. Those are just different groups of stars and nebulous sections within the Orion Nebula. They're simply just designated by letter. And yes, it's usually by order of discovery. So the blue star, I should show you right there. There's usually a blue star. There's the blue star right there. That blue star area is close to the trapezium. It's actually, well, the blue star is the flux center of the Orion Nebula. That's the flow of the energy coming out in all directions. The orange star, if we go back to the orange star over here, that's actually the center of expansion, what we call the OPBB1. It's a subgroup of the Orion OB1. So you have these stellar associations. They talk about how galaxies have stellar associations, a lot of O and B class stars. And the stars in the trapezium are actually part of that OB1 association. And they're broken down into 2 subgroups. There's the OB1A and the OB1B. And in that group, there's actually known as the Borsiano 1, which is what we call a kinematic open star cluster. And so what we get about that is that covers about 1 degree of sky. So that's twice the size of the full moon in the sky. It actually is very visible to binoculars. There's a common center where they can look at the stars, looking at the spectra, and they can see how they're moving apart for the speed. There's a lot of strong stellar feedback in terms of feeding back the energy from those stars that actually move around the stars to actually get them to move a bit faster from themselves, from each other. And then there is the interstellar medium. That's the dust and gas between the stars. It's like sort of like the galactic, it basically makes up the galactic winds. And this radiation feedback between the stars, actually as they push themselves out, they're using the radiation to create a larger and larger dust shell that's being pushed out by all that radiation. Okay, so this is actually comes from a three-dimensional program. So you can look at the environment, you can actually move around the areas right here. So the trapezium is right around here. Here's the Orion shell. You can see how the gas is moving out. You see how everything's expanding outwards. Because, I mean, even though, so here we have the three belt stars. Here's Beta Orionis, here's Gamma Orionis. So these are the stars that represent the large part of the constellation. And you can see how just the movement of these stars and the expansion of the gas and radiation overcomes any gravitational attraction, not only between the stars themselves, but between clusters of stars that are forming in that nebula. Okay, so this actually comes from an interaction program with Harvard University Facility of the Arts and Sciences at their Quantum Computing Center. So what you do here is you actually move around. You can actually look at the positions of the stars, the movement of the dust rings. You can see right here is the OPP near group. There's the Bereceno 1. So they can actually look at the spectrum of these stars. There's a bit of red shifting, so they can look at the velocity of these stars, cancel out the movement of our own solar system moving around the Milky Way galaxy, and see how all of these stars are all moving away from each other. All the stars in the Orion Nebula are moving away from each other, and they're moving around a point where they would have that big supernova explosion from an O-class star that no longer exists. Okay, so this represents that what we call the Hubble flow, that flow distance from the expansion center. This is in parsecs. Everybody familiar with the concept of a parsec? It's about 3¼ light years. So there's an old experiment where astronomers tell their students, okay, look at a star here on the 1st of January, see that same star 6 months later, and if it shifts across the sky with respect to stars further away by about 1 arc second, then it's 3.26 light years away. So a parsec is basically an arc second of a parallax. But here we get the velocity of the stars. So as we get away from the center of the expansion, the stars are moving outwards as a flow, increasing as speed. As they pick up that energy as it flows away, they pick up momentum. So they move further and further and further away from the Orion Nebula. Okay, now, here's very interesting, the inner realm, interpreting the environment. You have to map out the aluminum-26. That's the best way to try to map out these dust clouds, because you get the intense readings of radiation and infrared radiation from the dust itself, and also they have very huge signals in the radio spectrum. Yes, 21 centimeter, which is the radio waves for neutral hydrogen, is good. But if you're looking at dust clouds that are emitting much higher energy than the radio waves, it's best to look at the aluminum-26, because that way they can actually plot out the dust clouds and see the flow of energy as it pushes these star groups away from each other. So here we can look at the younger stars over here, the odds of no supernova. One thing is that this right here is we have the mapping of the aluminum-26, so it tells us what are we looking at here in terms of the behavior in the nebula. Well, down here we have no clusters with a mass of 6 supernova. Right here we have all the ages, looking at a distribution of the different ages of stars. And what we find here is that most likely we're looking at the ages of these open star clusters spread out after 1 or 2 supernovas. 50% of that energy is coming from that OPB1, and that indicates an age of at least 9 million years. So we're looking at groups of stars that predated the Orion Nebula that blew apart in the region where we have that OPB1. You had 1 or 2 supernovas, they make up 50% of the energy, and that's causing that spread out of that material and the spreading out of the Orion Nebula from its center. So we have at least 1 supernova that has occurred. We look at the dust itself. We have all our evidence. We look at the velocity of the gases. We look at the different, for instance, we look at the hydrogen alpha, the aluminum-26. We see the motion of the stars. We can identify the particular elements and how they change in concentrations. So we can see this gas expansion. So the OPB1 is the first group of stars to form. Then we get an H2 region that's heating up all the dust after the stars are born, that heats it up. Like you can have what happens here with the more massive star clusters is that you can have dust around it. You have reflective nebula, but if it's hot enough, it actually turns the dust into gas. The gas lights up. The gas expands. The stars are moving apart because they feel each other, they sense each other's radiation. Not only they're pushing the gas out and the dust sort of concentrates because of the difference between the speed of the dust and the faster movement of the galactic winds. That creates a shell, and the stars are moving away from each other. And so what we get is sort of a timeline of when did it go off, and it's very likely that it probably went off about, well, the numbers are still between about 2 to 9 million years ago. So there's still a lot more data that has to be collected. There's still a lot more unknowns, but it's pinning down between 2 to 9 million years when you had the first supernova explosion and the second one. But the Orion Nebula went through several stages of existence. And so we have that star-forming material over the next 3 to 5 million years. Okay, the mighty trapezium. I've seen A, B, C, D, and G, and H1 and H2. It's very rare. There's also an I star right there. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Most of the time you're seeing the 4. On a good night, you'll see 6. More than that, you'll have to have a much bigger telescope and very good skies. The top 5 stars, A and E, are between about 15 to 30 times the mass of the sun. So these are O and A. These are the O and B class stars. These are the massive stars. They're within about 1.5 light years from each other. So the radius of this is about 10 light years. So they're very close together like you would expect with an open star cluster. But we don't know the overall mass because there can be uncertainties in the masses of these stars. And you see, look at this. This is visible light. Here it is in the infrared. So look at all of these stars here. They're actually part of the trapezium itself. And most of that you can't see in a telescope, a visible light telescope, because all that darn dust is just blocking out all that light. You have to use infrared to pierce through the dust itself. So right there is where you can find the trapezium. The Orion bar is right there. So if you've seen this famous photograph, there's the Orion bar. There's the trapezium. This is M43 Demayran's Nebula. Here's M42. So it shows you where you are located. All right. So increasing in right ascension, that's sort of what we call our longitude in the night sky, going from 12 to 13 to 14 hours. That's how they catalog A, B, C, and D. The trapezium itself is part of a much larger cluster of even more stars. So there's a greater central cluster. It's 20 light years across. So there's an overlapping star cluster with the trapezium. There are 2,000, I talked about there's 6,000 members, but the inner part of it has 2,000 members with brown dwarfs. Those are what we call these low mass runaway stars. Not entirely red dwarf stars. These are just stars that are just, they could be like very low mass for the G and K class stars, for the orange stars and white stars like the sun. And there are accretion disks. So there are accretion disks literally being pushed away as they're forming stars and planets. So there's actually open star clusters within open star clusters and groupings of stars within groupings of stars. So it's not like you have an open star cluster and then the next open star cluster is over here. It's like you have shells of stars with overlapping star clusters that are being pushed out from each other at different rates. Okay, so the mighty trapezium, I'll say this, every one of the trapezium stars is a binary star. And usually what you get is an O-class star with a B-class star orbiting around it. So these are just very massive OB binaries. And usually with some of these binaries, they actually have binaries within binaries. So we actually end up having multiple star systems. So nearly every star is a binary system, and some of the binary companions also have a companion. But they're all O and B class stars. So you have basically you have got a big blue monster with a big blue monster companion with a big blue monster companion. So this is Theta 1 Orionis C. This is the big bright star in the trapezium. That's the great giant. We can only separate the stars by interferometry in the infrared. The OB class, these are all main sequence stars. The radiation is slowly disintegrating the Orion Nebula. So the bulk of the dissipating of the Orion Nebula is coming from this one star. The stellar winds are about 1,000 times the strength of the solar wind. So imagine having astronauts having to deal with that. And I'll say this, the sun's magnetic field isn't as strong as the magnetic field of this star. The difference is about 275 times. So very strong magnetic field. Some of these magnetic fields for these stars can stretch for some cases up to 300 or 400 AU. So up to hundreds of billions of kilometers. So it has a magnetic fossil field. I don't know if anybody's familiar with a magnetic fossil field. Usually what happens is that a star like the sun, the north and south magnetic poles flip back and forth every 11 years. With some stars, it doesn't flip at all. It maintains the same magnetic orientation. North magnetic field here, south here, and it doesn't flip back and forth. So that's what we refer to as a magnetic fossil field. It still retains the original field of the original orientation of the star. Absolute magnitude minus 4.9. So if it was 10 parsecs from Earth, it would be brighter than Venus. The C1 star, which is the central star, so there's C12, there's its companion, 39,000 Kelvin versus the sun being around 5,800 Kelvin. And it's over 200,000 times the luminosity of the sun. So imagine if the Earth was orbiting that at 93 million miles away. I mean, it would be very, very deadly. And it's very young, 2.5 million years old, but these stars at that scale do not last more than 5 million years. There's Theta 1 Orionis A. This is what we call the trapezium double-double because it's got a binary and inside there's another binary pair. So A1 is a B class. It's a spectroscopic binary, so you can't really separate out the stars. The A class star itself is a highly elliptical orbit. Possibly the A1 is potential T-Tauri star. The A2 star only orbits about 90 AU, which of course is further away than Pluto, but it's slowly gravitating towards the A1 binary. So that means there's the potential for those stars to collide together. And then there's a 4 solar mass star. It's likely a cool B class or a very hot A class star. You're going from OBA, it's going from high to low temperature. When the female astronomers, the Harvard computers of the late 19th and early 20th century, when they were doing these catalogs for ABC, they were doing it by the concentration of hydrogen in the spectra. All right, so this is where we have for the mighty trapezium itself. So this is Theta 1b. It's a multiple star system. It's a variable star. It's got an eclipsing binary. So that V right there is representing what we would call sort of like that's a dwarf star, and the 3 is a giant star. So we have a dwarf star. Our sun would be a dwarf star orbiting around a giant star, possibly a pre-main sequence star, which means that the B1 itself is still somewhat forming. And it's between about maybe 10,000 to 100,000 years in its age. So how do they know about the age of the star? Well, studying a lot of these O and B class stars and how their spectra has changed and a lot about stellar astronomy and physics, you can guess around the age itself. It's still highly uncertain, but this pair itself will likely last a few million years. So there's the curve of BM Orionis. That's the Orionis B. So there's B1, B2, B3, B4, and they're all orbiting around a center of mass. So if you want to do some interesting gravitational and kinematic studies for physical motion, these stars are a good example. This is there's Theta Orionis D, and then there's Theta Orionis E. Again, we got spectroscopic companions. Stars are orbiting close together. Some of the companions are A-class stars. Some A-class stars can gather a lot of mass around the environment and increase their mass towards becoming a B-class star. Usually they're in very close circular orbits. You have to use a lot of telescope interferometry to separate these objects because sometimes they're only like a couple of dozen milli arc seconds apart from each other. So I mean, I mean, you're really pushing the edge of optics when trying to separate these objects itself. And these are with big observatories with big 10 or 20 meter size radio telescopes to try to separate that out, or the 8 meter mirror telescopes with the very large array in South America and the Andes Mountains, trying to separate out these stars. I know that Theta Orionis E is actually listed in the new catalog of suspected variable stars. I don't know if everybody's familiar with that catalog. It's actually used to try to look at variable stars and see, we'll look at candidates for possible variable stars and see if those stars are actually variables and not the result of other types of effects within the nebula itself. Okay, believe it or not, there's every indication based on the dispersion of these stars that it fits with the possibility of an intermediate mass black hole, because not all the radiation and the mass of these stars are taking into account all the dispersion of what's happening with the dust and the movement of the stars. There's some indication by the flow of these stars that it fits with something around 100 to 150 solar mass intermediate black hole. And why is that? Well, it's like looking at all the movement of all the gas, movement of all the stars, seeing what type of mass is needed, what type of energy is needed to move this stuff around. And all the stars in the trapezium quite don't match that. There's actually a bit of a deficit, maybe some undiscovered stars, but there's quite a deficit in that range. And because we don't see anything, we might be looking at a possible black hole candidate. So it's probably somewhere in the central quarter parsec, so it's sort of moving around the trapezium. It's sort of interacting with the gas. How big can it be? Well, that would place the Schwarzschild radius itself would be big. That's about over 1.5 trillion kilometers. And the gas produced by the stars in the trapezium is a very low amount. So it's a very little amount every year. So it's about 100,000 times less than the mass of the sun. And the gas consumed by the black hole, looking at the radiation emissions, looking at the movement of the material, looking at the loss of gas, because there is a loss of gas they're noticing in the Orion Nebula, it's very minuscule, 10 to the minus 15th, but it is detectable. And the X-ray emissions itself coming from this region, because there's a lot of X-ray emissions that are coming from this region that are likely being formed by a black hole, is somewhere about 10,000 times that of the sun. So that's equal to the famous Cygnus X1 system, one of the first candidates for looking for black holes in the Milky Way galaxy. This is one of my favorite areas right here. This is the breakup of a multiple star system. So we have a trio of stars right here that were flung out of their birth system. There is what we call the Beckler-Nürnberger star. The I star itself is embedded in dust. Right over here is the X star. It's moving very fast, over 200,000 kilometers an hour. That's 30 times the speed of most of the stars in Orion. We don't know what the culprit is. It's a missing culprit, but we're likely dealing with a game of sort of gravitational billiards. That is, what's happening is that these stars are moving so fast, their fields of gravity are sort of knocking them around. Okay. So this is the Kleinmann-Low Nebula. That's the center point, is the Beckler-Nürnberger star. Very active star region. Lots of radiation, lots of dust and gas. We can distinguish that in the infrared radiation. This comes from the La Silla Observatory and from the multi-mode instrument there for the European Southern Observatory. This is a very interesting region. One of the things about this place is that it's very active in the far infrared. There's a lot of material, there's a lot of hydrocarbons being formed here, and a lot of planetary system candidates. In fact, this is looking through the James Webb Space Telescope. Look at that. It almost looks unreal, but every one of these is where you get basically the radiation flowing the dust out, pushing it against the stellar winds, and it's actually creating this, against the galactic winds, it's creating these sort of lumps of molds of material flowing outwards. And the radiation being emitted is 10 million times the output of the sun, 10 to the 48 ergs. And so we get all these front heads right here, which are all these stars that are forming with planetary systems, rich in a lot of hydrocarbons for forming organic material. Okay, so the Theta 2 Orionis system, I don't know if you've ever seen these three stars. I thought this is very interesting. because we learned a lot about the O and B class stars, the temperatures, the brightness, the separation. If you can ever see this in a telescope, there's the Orion bar. Right here is the Trapezium, and there is right there. This is the Theta 2-Eridanus system, because in old catalogs of stars before telescopes, it looks like a big spot of light right inside the Orion Nebula itself. So there's 13 components because there's a lot of double and triple star systems in here. You have to use a lot of speckle interferometry, that is, sort of cancel out the starlight in order to detect the star motion. And right here, with the Theta 2-Eridanus system, we have a lot of stars that are in orbital motion. So you look at the orbital motion, you can see the change in X-ray emissions. You can detect the change in X-ray emissions where you see the location of the stars, and you can actually determine that these stars are actually multiple star systems. The Stromgren sphere is very important because this is about looking at these bubbles. These bubbles, you think of radiation coming out in all directions. You get an electron orbiting around a hydrogen atom. It gets a lot of ultraviolet radiation, and it creates what we call the hydrogen alpha, beta, gamma, delta, your Balmer series, like you have H alpha and H beta filters. So you get intense UV and X-ray emissions from the OB stars. They take the hydrogen atoms, they stimulate them, they break up the molecules into individual atoms, and then of course it turns the dust into gas. The dust particles are like little solid particles in a microscope. It breaks up into gas, so it sublimates it. Now, it's not moving in all directions. It's actually forming these blisters. So most of these regions are like blisters. It's not like a sphere, a bubble of the dust turning into gas as it's being ionized, it's being broken up. The atoms are shedding electrons because it's the photons that stimulate the electrons and breaks up the dust into gas. But it's more like a blister rather than a sphere coming all about. So there's a lot of dust back here behind the Orion Nebula, and then there's this blister of gas heading out towards us. Okay, so the Bok globules, there's a lot of photodissociation. So a high massive star, a lot of radiation, it evaporates the dust at the end. The dust inside really condenses up. And so we get these Bok globules where we form stars. So these are miniature giant molecular clouds, a lot of silica, a lot of frozen carbon monoxide in this environment where the energy is not enough for the carbon to bond with two oxygens, it's just one. A lot of molecular hydrogen. These are cocoons for which you end up forming not only stars and protoplanetary disks, but we got a lot of water, a lot of amino acids, a lot of nucleotide bases. So we have many of the precursors for DNA molecules. So we go back to the Orion bar, we can see how the radiation is eating away at the dust. We have the denser material here. The dust is breaking up, we got the gas, and this is the stimulated radiation. And right over here in this upper image, we can see that front right here, where basically the dust is being broken up. It's turning into individual atoms and molecules, and it's literally causing this to literally disintegrate bit by bit from the radiation. In fact, we can see it right here. This is a famous image right here. So there's the cocoon of dust. You see the disk inside. That's about the orbit of Neptune right there. It's breaking up among the filaments. And so what we get right there is a star forming, possibly a planetary system. So going back to the Orion bar, look at the front right here. So this actually comes from the Journal of Astrochemistry. So these different colors right here represent different wavelengths of infrared with the dust material. So what do we get from the mid to far infrared from the James Webb? Well, we got acrylonitrile, methylcyanide, we got cyanopolonies. Some of these molecules here are actually the precursors for making synthetic rubber. And so we got a lot of these complex organic material, acetylene sulfide, cyanide. So we got a lot of complex molecules that are actually forming at the Orion bar itself in the breakup from the dust into the gas. And what do we get here? We're forming these flat disks from the accretion disks. All of these are little islands of intense dust within the Stromgren sphere, intense radiation that eats away at the less dense dust. But as the stars are forming, they're coalescing the dust around them, and we get the shockwave material right here. And either we get them as luminous or glowing, or they're dusty, dark, dusty silhouettes. So they'll either have no planetesimal systems or they'll have large planetesimal systems, which means if the radiation is intense enough and the dust is not very dense, it's just the star by itself, maybe with a companion. Or you get a star and a companion star, a binary, and planets forming around it, or planets forming around a single star. There's about 180 of these have been mapped out in the Orion Nebula. And this is just many of these, and we can see the dot of light in the center of many of them. Okay, so what this shows here is the ionization front. There's a concept called Herberg-Haro objects, where these actually emit jets of gas. Material falls into the star from the accretion disk, but the radiation is so intense that it clears out the area. And some material gets stimulated by all the radiation from the newborn star, gets shot out as jets. And that jet compresses against the stellar wind, against the dust, and it forms those bright patches. So we get the ionization fronts right here against the galactic winds. That looks like a flying saucer right there. But there's the dust, there's the brightness in the gas itself. And right there, that's that other famous image in the color itself right there. So that brightness is coming from the Theta 1 Orionis, the Theta C star from the Trapezium C. Now, one thing is that you can actually look at different, for instance, right here at this frequency, just around 2 microns, as you penetrate deeper into the dust itself, you find that the dust actually protects a lot of the water ice from disintegrating, from being broken up, the hydrogen separating from the oxygen. So as you penetrate deeper into these propellets, we find a higher concentration of water, the stronger that signal right here. And that indicates that inside that inner propellet would be the best candidates for forming water planets, or planets rich in water. Now, brown dwarfs. 20 brown dwarfs have been discovered, many of them right below the critical threshold for nuclear fusion. In fact, many astronomers talk about how the limit is about 8% the mass of the sun. It's actually around 6.67%. So many of them are just below the threshold where you get deuterium rather than hydrogen fusion. So it's not sustainable. So there could be future confirmations of even hundreds and hundreds of brown dwarfs, more than red dwarfs, forming in a nebula. So a nebula will form a lot more brown dwarfs than red dwarfs, and form a lot more red dwarfs than all the other stars. So these are all the candidates for the reddish stars, free-floating brown dwarfs, water or no water in the spectrum, free-floating planets. They're what we call these jumbos, these Jupiter mass binary planets, where you get 2 Jupiters orbiting around each other, but they form out in the nebula without orbiting around a star. So you get a case where planets can form without having to orbit around a star. So we get free-floating planets, a lot of water-rich, faint, ultra-faint brown dwarfs. They will not have continuous deuterium fusion because you can burn heavy hydrogen at a lower temperature than regular hydrogen, but it's not continuous. Okay. And within the Orion Nebula itself, many unsolved questions, many publications that have not met peer review approval, but one of these is the candidates right here. 40 of these have been found. Jumbos, 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 jumbos. So these are gigantic Jupiter-sized massive binary objects, which means you got pairs of Jupiter mass bodies. So these are like Jupiter-like planets, binary planets forming around each other, but they formed inside the nebula, but didn't form around a star. So now we have indications that planets can form in nebulas, possibly without having to be born around a star. So you get a lot of brown dwarfs, you get a lot of red dwarfs, you get a lot of free-floating planets before you get other types of stars being born, as well as planetary systems around a star. So possibly rogue binary planets. It's not 100% certain about this. So there's a lot more data that has to be evaluated, but looking at the light and how these stars are how these objects are moving around each other, you can't really classify them as stars or brown dwarfs. So it's like looking at a different type of interstellar object that's been discovered in space. So this is the mapping structure of the Orion Nebula. I don't know if anybody has the Atlas of the Messier objects, that nice book. It actually gives you, it's interesting because they give names to all these structures right here. The Proboscis Minor, the Proboscis Major, the Huygens region, the trapeziums, the fish mouth, the subsidiary branches, the palm, the ink spot, the Orion bar is right over here. So you actually can name these features the same way you name features on the surface of the moon. And the mapping structure. With the proboscis major of the Orion Nebula up here, a lot of stellar bodies, some of them down to like only 2.5% the mass of the sun. So that small of a size, you're looking at a lot of perhaps super Jupiters and perhaps literally small scale brown dwarf stars. And that's the proboscis major is this region right here, not far from the Orion's bar. Okay, so we're mapping structures of the Orion nebulas. So when you get a change in the density of gas with temperature, has anybody ever seen that effect up in the stratosphere? Well, guess what? We see the same turbulent effects. So we talk about Kelm-Helmholtz instability. So you get very dense cold material. It comes against a very thin warm environment of loose gas versus that of the dense material. Sometimes the temperature is inverted and it causes material to swirl because just the symmetric motion of mass and energy. We can see that there in the eruptions when we're looking at it in hydrogen alpha or in X-rays with eruptions in the sun's photosphere and in the convection zone. But look at right here. This is coming out of these bow shocks that we see in the Orion Nebula, where we get the thin environment here of this gas from the radiation, and then we have the colder, dense dust. And when that gas is trying to eat its way into the dust itself, it symmetrically moves around and creates that swirling pattern. There's a simulation right here, and we actually see this on Earth, but now we're seeing it not only on the sun, but also out in space. So the bow shocks, right here, we get the bow shocks itself. So the hot stellar winds are evaporating the cold, denser gas material. So we have dense gas, we have denser dust, we have the not so dense gases, and the material goes from subsonic to supersonic in terms of we can actually take the radiation, compare it to sound waves, and we can measure the speed of the material, and we get a fast stream of charged particles, and it forms these L-Orionis stars with this shock wave of change in brightness, and we see that all around the Orion Nebula itself. And the Herbig-Haro objects, again, you get an accretion disk, a disk of dust around a star being born. The material falls in the gravity well of the star, but the radiation is so intense close to the star itself that some of the lighter elements, the hydrogen and helium, and the carbon get stimulated and it escapes out as jets of gas that is along the rotational axes of the dust itself. So it shoots out as this plumes. The plumes spread out, but they come in contact with the galactic winds. It creates a shock wave. It builds up dust, but it lights up. So when you think about a Herbig-Haro object, you're not looking at the accretion disk. You're looking at these blooms right here coming from the star itself. And we have lots of these in the Orion Nebula. Right here, this is the change from 1995 to 2015. That's Herbig-Haro 505. You can see the plumes there. I even located here in the Orion Nebula, so we got the coordinates of these if you want to go and check them out. So we can map out a lot of these Herbig-Haro objects and actually try to go observe them in a telescope. I don't know if there's an astronomical league program for that, but that would be very challenging. But one thing is that we can actually, with some of these, look at the hydrogen alpha, look at the sulfur 2, charged sulfur, and look at how these plumes are moving over several years and actually give them knot designations. This is from the James Webb Space Telescope. So you can look at all the dynamics of the differences in the galactic winds as they move around the gas at different types of elements at different concentrations. There's a bit of a movement right here. You can see that with HH47. You can see how that material is moving back and forth. So those are two lumps coming from a central star right there that's sort of masked in a local nursery or a local hub of dust. But the radiation is able to push out and create these shock waves. So stars will form out of the clumps of hydrogen and helium. They'll concentrate, they'll accumulate water and organic material. There's a buildup of, I tell students, you take a bunch of dust. It gathers together with electrical forces. It builds up, gravity takes over. The material collapses under its own mass. Eventually what happens is that particles start to collide. There's a buildup of thermal energy. Nuclear fusion takes over. But depending on that, you'll either get stars, brown dwarfs, or planets. So you get that gravitational energy from the mass collecting together, turns into heat, turns into nuclear fusion. And then there's the angular momentum that's building up the, collapsing the disks themselves, conserving the energy that's being released from these reactions. and potentially forming planetary disks. We want them to collapse in so that the lumps of dust will sort of squeeze in to form planets. All right, I know that's a lot to chew, swallow, and digest, but you can look at this right here. I always think that as a glowing flying saucer traveling through the atmosphere, but it's strange and wonderful. We're just beginning to realize there's more to the Orion Nebula than just seeing dust and stars. So it's a never-ending journey through the Orion Nebula. In fact, many of the new concepts of stellar evolution, of nebula astrophysics, and planetary formations are coming out of using the Orion Nebula as an observation laboratory to gather data and do a lot of science and evaluation and a lot of data science modeling, which is what I like to do. Any questions?
Yep.
Yes.
When I observe the Orion Nebula,
Mhm.
I fancy I see kind of a greenish tinge. Is that possible?
Yes, it is. I mean, it depends. I mean, the greenish tinge is coming from, it's coming from probably from the oxygen itself, because you can have double ionized oxygen in the Orion Nebula. It's not very common to see that depending on the sky conditions. It's not always, I mean, usually with O3, there's like two frequencies. There's one for blue-green and there's one for cyan. You see that a lot with planetary nebulas, more in the blue. But with the Orion Nebula, it's a lower energy of that double ionized oxygen. That's where you're probably seeing the green, because it'll instantly react with carbon to form carbon monoxide.
It's a very faint green. It's nothing.
Yes, it's not going to be as intense as a planetary nebula.
Thank you. Yep.
It's a lot of mass, but it's spreading out over a much greater volume. Anybody have any questions? Yes.
Hi. Um, this laboratory, as you call it,
Yeah.
right? It's so close that it is very convenient, so to speak.
We're lucky to have it.
Lucky to have it. Yes.
It's not one of the only ones. Other areas have been the Eta Carigni Nebula, as well as the Lagoon Nebula. There have been studies done with the Tarantula Nebula and the Large Magellanic Cloud and the Triangulum Nebula in the Triangulum Galaxy. But the Orion Nebula is close enough because it's just of the distance.
Yeah. And these are nebulas are all part of the Orion arm.
It's in the
galaxy,
Orion
or-
spur.
Oh,
Yes.
yeah.
It's a fragment between two arms in the Orion, in the Milky Way galaxy.
What surprises me is the high density of the stars that are inside of.
There's a lot of stars there, but again, it's radiation that's pushing out the stars when they pass by each other. There's a lot of gravitational slingshotting. So again, you got a lot of there are a few star clusters in there that are pulling themselves apart because they're undergoing a gravitational billet. So they're literally somewhat gravitationally smacking against each other and just flinging away from each other. So it's a very bizarre thing.
Thank you.
I wouldn't want to be in the middle of that gravitational billiard game.
Eventually, as all the material is coalescing into stars and planets, eventually the nebula will end up being a set of star clusters, or what?
Okay. Unlike in nature, well, I know we talk about recycling things 100%, but most nebulas probably won't recycle more than 30% of their material. So 30% of the raw material that came from the stars that blew apart to form the nebula actually form into planets and I guess discovering binary planets and other types of objects. That number will probably go up, but it's going to be around 30% because the radiation eventually is so intense it's going to dissipate that nebula into these and break apart into these giant molecular clouds, and all you have left is just a bunch of reflective nebula like the Pleiades. But the stellar nursery is going to break itself apart, and only maybe a third of the material will turn into stars in any one nebula because just the radiation will. Remember, the whole thing is blowing apart faster than the ability for every molecule in that nebula and every atom to coalesce into some star or planet or some other type of a binary, a stellar-like object.
Yeah.
Okay.
Peggy asks, oops.
Peggy asks, are most jumbos found next to the trapezium?
The jumbos are being found in the area around the trapezium, but also in much further areas from the trapezium in different regions around the nebula itself. But the largest concentration is within that Stromken sphere that's usually powered by the brightest star in the trapezium, Trapezium C.
Awesome. Yeah, thanks. I had a question. So
Yes.
the cosmic keyhole, we were debating that last week.
Yeah.
Is it dust, or are we like literally looking through everything out of space?
You mean with the Orion?
Yeah, the cosmic keyhole, you see like
Oh, that's just a lump of dust.
it's just a lump of dust?
Yes, I mean, the denser the dust, the longer the wavelength of radiation, of infrared radiation you need to penetrate it.
Yep.
So,
So it's blocked. Yeah.
yeah. But you can see the light of the star behind it.
Yep.
How does the mass of the Orion Nebula region compare to the Carina area?
Oh, gosh. There's a wild estimation about the Orion Nebula itself in terms of its mass. I will say this, it's one of the top massive nebulas in the Milky Way galaxy.
Compared to Carina, several times larger?
I would say it's probably, well, I only know it in comparison to that of the, well, is it on the same scale as that of the, let's say, the Tarantula Nebula? I would say so, because I mean, the region spans literally for thousands of light years. So when you see the Orion Nebula itself or the Horsehead, you're only seeing snippets of the whole thing.
Yeah, so I didn't have a question, it was more of a comment, but you raised the question of an astronomical league program with regard to the Herbig-Haro object.
Yes.
So I actually looked it up real quick. There is not, in fact, a program specifically related to Herbig-Haro objects, but just sort of related to this, there is the Stellar Evolution program,
Yes.
which is just broadly related to stellar evolution. So if you're interested in stellar evolution, that is a option. And just by the way, that program was developed by our very own Bill Pellerin.
And what's interesting is that when you look at the nature of those Herbig-Haro objects, they can give details as to the evolution of those stars occurring inside the accretion disk if you can't observe them directly.
More questions?
Nope.
Online, more questions? All good? Yeah.
Well,
Thank you
it.
so much. Yeah, thanks so much.
Thank you.
All right. So thank you so much for the great talk. So the next meeting is next month. So that will be March 6th, also at this location, and also like hybrids like we have now online. Oh, thanks. Yeah, thanks. I forgot to put my camera on. And also don't forget about the novice meeting and all the other events that we just listed. Bill, you had a question? Yes, so the novice meeting will remain on Zoom to make the barrier of entry even lower for people to join, and then this meeting will always be in person and on Zoom. Of course, we encourage you to join us in person because, as you see now, it's just really nice to be here in person again. So, yeah, see you next month. We have the place for at least another half hour, so hang around a little bit. If you didn't do that yet, put your name, please, in the list in the back so that we can kind of see how many people we had joining today. That's for our statistics. But yeah, that's it. So thank you very much, Justin. Thank you so much again for the great talk. And yeah, Professor, thank you so much for hosting us. Fun. So yeah, see you next week, month. All right.
Next week.
Well, and next week too, on the prime night, of course. Yeah. Great. Thanks. Bye-bye.